Okay, thank you very much. You honour me greatly with the Michael Hoskyn lecture. In preparation for this talk, I went and I bought his book. I read his biography of the Herschels. And what really touched me was that he stated that the more you read about the Herschels, the more you like them. And I found that was definitely true. And I inspired me to go to Bath, to go to the Herschel Museum. And I was really intrigued to see that there in the floor, you could still see the damage from where Herschel was casting his telescopic mirror and it went into meltdown. Now, I'm going to try and not damage the floor today, and hopefully I won't go into a meltdown, but I'm going to try and cast you an image of Riccioli, that he was a loyal and likable polymath who excelled in the fields he worked in. And he's quite a mystical, a mysterious figure who's quite difficult to stomach for the modern mind. Why is it that this person who, with unprecedented accuracy, measured pendulum swings and measured the gravitational acceleration on the Earth's surface G, why is it that this person who came up with the idea of the Coriolis effect, why is it that this man who, together with Cassini and Grimaldi, verified Kepler's elliptical orbits, why is it that he was a geocentrist? So we're going to talk about him. If this works. There we go. Just about me. I have a background in theoretical physics, bachelor's. I've studied science and religion in a postgraduate diploma, and I'm working on translating Riccioli's Almagestum Novum, which is his phenomenal work from 1651, which was, he thought it would be the textbook of astronomy for all time. Most people have never read it or even heard about it. I've worked in software for a long time, and I'm an amateur astronomer and astrophotographer with a 12-inch Dobsonian, and recently I inherited a LX200 from amateur asteroid hunter Alan Carhill, which I'm very grateful. And I became interested in Riccioli from my astrophotography, taking photos of the moon, and I was trying to match the craters with the maps. And what was it? It was so strange that a lot of these names were priests and other weird figures who I'd never heard of. And I thought I'd look it up where this came from. And Riccioli is the man who named the lunar craters. We take his nomenclature and we've improved upon it over time as we found new craters. So why was his book never translated? We don't even know the reasons for the origins of most of these people. And I found that fascinating, which is why I started learning Latin to try and translate this book, and got into all sorts of weird things. Who knew 5 years ago that I would be studying astrology in my spare time, something I don't believe in, but decided I needed to study to understand his works. I also declare I am a Catholic, so in this talk, we are going to be touching some subjects that are controversial for the relationship between science and religion. So please do challenge me on any bias you may think I have at the end of this talk. Okay, so let's talk about the background just before Riccioli. What was going on? This was quite a difficult period of unrest, but also a time where astronomy was becoming important. Why? We had the age of conquest, the age of sail. You needed astronomy to find your location, to find your longitude, your latitude. A lot of these were difficult problems. They had to be done on board a ship to keep your men safe. We had the Reformation and the Counter-Reformation. This was a period where you couldn't say everything that you wanted to say necessarily, where Protestants and Catholics were at each other's necks, where there was some dissent and some repression. We had a long-standing problem of the alignment of Easter with the spring equinox. And in the 16th century, Gregory XIII, the Pope, brought in the Gregorian calendar and tried to align the whole world to have a new timekeeping system. This was itself spurious. Protestants did not want to take this on. This was a weird Catholic idea. But this was important for astronomy. Astronomers were put forefront. They were given money to try and figure out how to predict Easter correctly. We are here today on the second Sunday of Easter, and it's very fitting that we are talking about something, that is so related, because Easter and the calculation of Easter is why this man got funding, why other astronomers of the time got funding in the Papal States, and it relates to some of the controversies in his life. And of course, astronomical advances were becoming important to the church. Why? Because advanced sciences, the technologies that Europe had found, were ways of missionaries to make their way into foreign courts and to start persuading foreign rulers to adopt the faith. So all of these are factors that are just geopolitics. Of course, in astronomy, we have new advances just before Riccioli. Copernicus, the century before, was proposing a new heliocentric model. It was a mathematical model. And we need to put this in perspective. The Ptolemaic model before wasn't always believed strongly. It was, in ways, reconciled with Aristotelian cosmology. And not everyone believed in the Ptolemaic model necessarily. It was there to save the appearance of the phenomena of why the stars in various places, but people didn't always believe in it. And when Copernicus's De Revolutionibus was published, a lot of people started adopting his model without actually believing it. People were not easily convinced that the Earth was moving. Your personal experience, if you don't know that the Earth is moving, doesn't give you any feeling of movement. Aristotelian cosmology gave a reason as to why things were they were, with a strong focus on the Earth having a pull downwards and everything moving around it. This wasn't something easy to shake. The only way you could shake that is by replacing Aristotelian cosmology entirely. And we then see advances in astronomy with this kind of weird framework of mishmash. Erasmus Reinhold released the Prutenic tables, which were the latest tables in astronomy, and they were built with a weird kind of framework where he was a geocentrist, but he was trying to use Copernicus's model to predict where various objects in the sky would be. Ignazio Danti, we've got to mention him. You probably haven't heard of him, but he was one of the first to start building what are called church meridiana, or meridian lines. These would be lines in the floor of a church. You'd poke a hole in the roof, and you could use this as a huge observing device to see how the sun moved and try and start to calculate Easter. Tycho Brahe, he was also a geocentrist. He argued that since Copernicus's theory suggested if the Earth moves, you should be able to measure a stellar parallax between the stars. And since all his attempts to measure it had failed, therefore, the Earth has to be motionless. And when he put to paper his Tychonic model, he was actually putting on paper what many people already believed. They wanted to use the Copernican model, but they were not convinced that the Earth moved. In 1609, Kepler wrote the Astronomia Nova. This is going to be key to our understanding of what happened with Riccioli, because Kepler introduced the idea of the elliptical orbit of Mars and elliptical orbits of the planets in general. Before this, we had epicycles. This was the first time epicycles were being dropped. And This was not immediately accepted by everyone. But reading Astronomy Nova recently, I did have the feeling, when you read it, this almost feels like Newton's works. The way he writes about the magnetism, the pull between the sun and the planets, he was so close, and yet so far. We have Galileo, who started publishing works on astronomical findings, Jupiter's moons, phases of Venus, and all his other works, the mountains on the moon, sunspots. So finally, they had to discard the Ptolemaic model, but the Tychonic model was not discarded, because all of Galileo's observations were compatible with the Tychonic model, which was mathematically equivalent to the Copernican. Okay, let's go into a bit about the conflict leading up. Of course, we had the heliocentric, geocentric debate, and this wasn't always pretty. Galileo was put under house arrest. It wasn't so simple to be a heliocentrist. The rules from the church were that you had to hold heliocentrism as a hypothesis. You could still, in theory, research it, write about it, and so on, but you certainly couldn't declare yourself for it. But there were other conflicts at the time that are often forgotten. The difference between realism and instrumentalism. Some people believed strongly that heliocentrism or geocentrism were real, but this wasn't the necessarily only position you could have. Pope Urban VIII was an instrumentalist. He wasn't sure which one it was, really. God could have done it either way. We can't confine him to a certain way of thinking. We have Hermeticism and modernism. Hermeticism was the idea that the past had knowledge that we have to source from, that the ancients knew something more than we know, whereas a modernist thought was, we know better than anyone in the past. And this was a form of conflict. You have rationalism, empiricism. Some people were empiricists. They wanted to measure everything. Some people didn't think you should measure anything at all, and that this was forlorn. And astrology is an interesting one. Astrology was divided into different types. You had judicial astrology, which was the kind of astrology of horoscopes, of nativities. You would take someone's birth date and you would try and figure out what their life would be like. Judicial astrology, to some extent, was condemned by the church at various points. But there was also a different kind of astrology, natural astrology. Just the idea that the tides are driven by the motion of the moon and the sun, or that medicine is affected by it, or the weather. And these were okay, but judicial, not so much. Although, we say this, while there were condemnations, these weren't always very strong. It could be a condemnation of a particular thought, a fatalistic thought, that the stars just defined how things were. And this would contradict the Christian idea of free will, which was a no-no. But perhaps the stars could slightly move us, affect us, but not necessarily define us. This was more acceptable. And we see that despite any oppression of the astrologers continued to be hired by leading churchmen, by rulers throughout the early modern Europe. An interesting one, of course, is Pope Urban VIII, who, while he condemned Galileo, he was also one who had issues with astrology. He wrote a papal bull against astrologers, while at the same time hiring Tommaso Campanella, an astrologer, to protect him against other astrologers, because they had predicted his death around the time of the 1630 eclipse. And so convinced were some people that this would happen, that some cardinals started thinking and talking about who would be his successor. We can think about this today with the new Pope dead, with Pope Francis dead, and there's already a lot of difficult conversations in the church about who's going to succeed and is it going to be good for everyone. Imagine that happening before you were dead. And let's talk about Jesuits, because Riccioli was a Jesuit. He was a Jesuit priest. And the role of the Jesuits is important. The Jesuits had been formed as almost a militant arm of the Catholic Church. They were subject directly to the Pope and were to follow his every will. They were devout. They were strong missionaries who were sent out to convert the unconvertible. In 82, Matteo Ricci was in the Chinese court, and he was starting to influence the Chinese. The Japanese, too, had Jesuits in their courts. It didn't always go so easily. In 1614, Jesuits were ousted out of Japan under the Tokugawa shogunate. In an odd way, Japan ended up being one of the last countries to accept heliocentrism because they rejected Western thought and Catholics and Protestants, of course, as well. The Jesuits were reformed by Christoph Clavius in 1593. He turned them into a mathematical powerhouse by making their studies involve mathematics and astronomy. And in this way, we find Jesuits in the history of science through most of the 1600s and 1700s, and even today. Okay, let's talk about Riccioli. So Riccioli was born in 1598 in the Papal States. He studied in Parma under Biancani, another Jesuit scientist who taught him geometry and on the Sphaera Mundi. Biancani was critical of Aristotle. This was quite unusual. Not everyone did, and this would have been considered quite controversial. He was ordained in 1628, and he started teaching in Parma. He didn't just teach astronomy or mathematics. He did teach Francesco Grimaldi, who became his great companion in science. He also taught other people, such as Daniele Bartoli, who was declared later the Dante of Italian prose, a great writer. What happened later was that he moved to Mantua in 1633 and started studying pendulums. This would be something that would be instrumental to his later successors. In 1636, Riccioli became the professor of theology in Bologna. This might sound great, but it wasn't necessarily great for him, in his own thoughts. Why? He had been moved out of Parma because he had befriended Francesco Grimaldi to a great extent. I think what was really happening was that Riccioli easily made strong friendships with people who shared his interests. And the Jesuit leaders didn't want people to be favored. So they didn't like the idea of favoritism in a college at university, that one student could be preferred over others. They decided this wasn't great, and they moved Riccioli out. Riccioli in Bologna benefited from this, though. He did build an observatory in Santa Lucia, which was a Jesuit college, and there he equipped it with telescopes, quadrants, sextants, and then he built a great grand meridiana in the church of Santa Lucia. Unfortunately, none of this is left since the Napoleonic armies stayed there. It was 23.7 meters high. The idea of this was that churches were built really tall, and by having a hole in the ceiling and lines across the floor, you could study the sun's motion through its light passing through that hole that was more accurate than any sextant or handheld quadrant. Okay, let's move on to the measurement of G. In 1640, Riccioli started to think physics. He was given Grimaldi to work with again. Their partnership was most fruitful. They could study things to great effect, and they did so for many years. The measurement of G was unprecedented in the amount of effort that went into measuring it. What was he doing? He was measuring the amount of pendulum swings in time to try and get a pendulum just the right length so that it would be 1 second between swings. And now I want you to try and imagine how many of your friends could you get around your house and watch a pendulum swing for 24 hours and count every single swing. Well, I don't know if they were his friends or whether he had some kind of power over them, but Riccioli swung first for 6 hours, measured 21,706 swings. On another day, he persuaded Grimaldi and 8 other Jesuits to measure a full 24 solar hours of pendulum swings, counted 87,998. It was a bit off. Well, got to lengthen the pendulum and try again. Another day, they measured pendulum swings all day. And, but it wasn't quite right. 86,999, it was still off by 359. That still wasn't good enough for him. He shortened it, which was actually the wrong thing. He should have lengthened it again, so it was a minor mistake, but not for want of trying. And once again, he measured it with Grimaldi and, paradoxically, Father Zeno. On 3 separate days, they measured it again with more swings. And he finally accepted this last final length that he changed again to make it more accurate. But he didn't measure it this time. I think everyone was sick of him by that point. But with this, he then calibrated a smaller pendulum that would oscillate multiple times in the length of the 1 second pendulum. And then he got a whole bunch of Jesuits to sit with him, and together they were singing Do, Re, Mi, Fa, Sol, La, Si, Do, and in this way you could time it with the pendulums. Do, Re, Mi, Fa, Sol, La, Si, Do, and you could actually get an even shorter length. And in this way, he could actually test more accurately the subdivisions of time in that. And with this, he calculated the free fall of objects and measured G to be 9.36 meters per second squared, which is a bit off, but not too far. It was certainly the first measurement. And when he did this, he was impressed. He had proved Galileo's laws of free fall, that it fell with proportionally to 1 over the square distance. Now, he was so happy about this. He ran to meet his friend Bonaventura Cavalieri, who was one of Galileo's pupils and a great friend of Riccioli. And he ran to tell him. Cavalieri was at the time in bed. He was sick. He was frequently sick and died soon after in 1647. This was a sad time for Riccioli, who had made great friendship with him, but he at least had this one moment of joy together. However, another experiment he did. From a Torre a Sentinel, a tower, he dropped a lead ball and a wooden ball to test whether Galileo's theory that 2 balls of equal size, of equal size should fall at the same speed. And with their singing of Do, Re, Mi, Fa, Sol, La, Si, Do, they found that no, they did not land at the same time. We, of course, now know why, because of the air drag and so on changing with different weights. You don't get the same speed of balls falling unless they're in a vacuum. But they considered this evidence against Galileo. In fact, Grimaldi was so shocked that there was such a difference that he thought that Galileo had covered up the fact that they fell at different rates intentionally. After this, there was a period where Riccioli ended up working in astrology. In fact, there was one quote of him saying that without astrology, we would never be able to sell astronomy books. And I think he was himself quite opposed to astrology. He certainly criticized it heavily, but he also sourced from astrologers. And this really annoys me because when I'm reading his works and looking up what he writes, he often, for example, cites the birth dates or death dates of astronomers, which he's clearly taken out of astrological books. And the problem with this is astrologers would sometimes change the date of people's birth dates or death dates to try and fit their narrative of what that person's life looked like. So this is problematic and something that has often caused me headache. It's bad enough that the calendars were in conflict, that some people's dates were in the Julian calendar, in the Gregorian calendar. In the English calendar, you also have the fact that the year started in April, just like our business year today. But this was the whole year started then. So he worked for Malvasia, who was a senator in Bologna at the time. And Malvasia wanted to predict storms using astrology. And together with Cassini and Grimaldi, they worked there. And on one fateful night, their prediction of a storm predicted an actual storm. But it turned out that this was a mistake, a typesetting error. I think Riccioli probably got disenchanted by this entirely, but Malvasia was persuaded that this was proof that astrology could work for predicting storms. And this was great for Riccioli and others who were funded by Malvasia from then on. So let's go to the Almagestan Novum. This was a project that Riccioli wanted to complete. It was supposed to be the completion of Ptolemy's work, the Almagest. And he wanted to write a new textbook that would cover all the new discoveries, the telescopic discoveries, all the new measurements, everything that had been found about astronomy. He wanted it to cover the new processes of lens grinding and so on. He didn't complete all of it, but even the bits that he completed are phenomenal, huge. There's 2 books this big. They're written in tiny print. It's a headache for me. Fortunately, you should be able to read it in English as I translate it. But this was a book that was difficult even at the time when people did speak Latin. Every astronomer would have bought a copy if they wanted to look serious, but I doubt many of them had read the whole thing. So Grimaldi had some issues with it, notably because of its size. When he submitted it to the censors, they asked him to give them a summary of the methods he used and the tools he had completed his observations with. And he said, well, no, that's actually going to result in me writing a whole new book, so maybe let's hold off on that. And they were a bit shocked by the amount of money he needed to complete the project. Printing was not easy then. Printing in the 1600s involved people putting every single little letter for typesetting in a slide and then doing that for all the lines and then printing out the pages, each one individually. This was a huge amount of work and it required a whole team for many years to complete this. But eventually Riccioli was allowed to work on this full time. Unfortunately, perhaps for everyone or for us, I don't know for whom really, but Riccioli didn't complete the whole work, most likely because of his other interests and other projects, which often filled up little gaps in time between the time he should have actually been doing his work. Let's look at this frontispiece. The frontispiece is it's right at the front of the book, and actually this covers a lot of what Riccioli's ideas were, what he believed was true at the time. We can see here Ptolemy on the ground, his model rejected. No one believed in Ptolemaic model anymore. He says, "Erigor dum corrigor," which I translate mostly as, more or less as, I am raised while I'm corrected. Now this is perhaps whimsical, but I wonder if this is where the statement to stand corrected has originated from. There are no mentions of such a phrase before. The first mention in the English language is John Dryden's Maiden Queen. The idea that when you are corrected, you are improved upon. And I'm so grateful to be here with all of you today. You can correct me on anything I say, and hopefully we can learn more together. But Dryden certainly showed that he might have come across this book. He wrote another book in 1660, the Astrea Redux, which covers, which if you see on the right, there's Astrea, goddess of judgment and the stars, Greek mythology. And she's holding this scale. She's weighing things. And perhaps Dryden was inspired by this book to write that poem, which was for him a moment where he felt judged because he had backed Oliver Cromwell, and now had sided with King Charles, who had just been returned, King Charles II, who had been returned to his throne. On the bottom, we can note the coat of arms of the Grimaldi family. This is the family that then, and still today, run Monaco, the tiny little city-state on the border between France and Italy. A curiosity of the Almagestum Novum is that in it, of course, Riccioli included a family tree of the Grimaldi family. This was a slightly odd family tree in that it was for the first time ever connecting French royalty to the Grimaldi family. Why on earth was that in there? Well, Cardinal Grimaldi, a relation of Francesco Grimaldi, his collaborator, was actually their patron as well. And by publishing this family tree in an astronomical book, they could get this family tree into every court across Europe and persuade everyone that indeed the Grimaldi family were related to French royalty. And in an odd way, this astronomical book allowed them to forge an alliance with France, with Monaco. I wonder if this happens in any books today. Here we have on the left Argus Panoptes. He was a mythical giant with many eyes. Riccioli gives him a telescope and he's observing the sky from his knee. Why am I talking about this? Well, Riccioli wasn't just an astronomer. He was fascinated by history in general. And one of the strange things about him is he had a very rationalist take on history. He looked at some of the ancient Greek and Roman authors who had believed that the mythical figures of Greece and Rome, were perhaps real people who had been deified. Perhaps some of them were astronomers. He thought Atlas, maybe he just built the first celestial globe, and that's why he was holding up the heavens. And other such ideas. So this is a bit strange. He had this rationalist take on history. But while rationalist, I also found a few difficulties with this, in that, for example, he still thought the Minotaur was real, and he put a date on when Theseus had fought the Minotaur in another book, but more about that in my book. Anyway, here we have Astræa's judgment, and here we finally see Riccioli's model on the right. On the left, you have the Copernican model. It's being weighed against Riccioli's model, and Riccioli's model is found to hold more weight. His model has Earth at the center, the sun going around the Earth, and then the other planets, well, not all of them, going around the sun. It's Mercury, Venus, and Mars going around the sun, but then Saturn and Jupiter are going around the Earth still. So the Copernican models, they were not the only models around around the time. There was also the Capellan model. The Capellan model had existed since about the 5th century, perhaps before. And this was a model with just Venus and Mercury going around the sun. This was clearly something that had been considered a long time ago. But by this point, it was pretty clear that Mars was going around the sun, and Riccioli was certainly convinced of this. He wasn't convinced of Jupiter and Saturn, perhaps because of the length of time it takes to actually measure a full orbit of them and figure out what they orbit around. Last bit. Why was he a geocentrist? So we'll come back to this, but he was convinced by two main arguments, one of which was the lack of stellar parallax, just like Tycho Brahe, and secondly, he predicted there should be a Coriolis effect on a spinning Earth, and there had been none detected so far. So surely the Earth didn't spin. Okay, up the top left, we have the planets that orbit the sun. Mars, Venus, Mercury. And on the right, here we have some of the other discoveries of the time, which we can see. Jupiter's moons, Jupiter's stripes, Saturn with its ears. We have the moon with craters, with mountains, and we have comets. Now, intriguingly, looking at that comet, you can see the tail faces away from the sun. I'm not sure you can quite see it, but in the larger image, you can see it, that it faces entirely away from the sun, like we know it does. And the comet is coming out from under the Earth outwards. There had been a big debate about whether comets were supralunar or superlunar, whether they were below the orbit of the moon or above. Tycho Brahe had calculated that they were above the moon, and this was pretty much the consensus at the time. But some scientists did not agree with this. Notably, Galileo argued that comets were below the moon, and that perhaps they were even an optical illusion. Another one was Scipione Chiaramonti. Now, this is one of the things that I hope one of you can tell me about, because Scipione, he wrote a long mathematical book with lots of measurements, and he thought that it was under the moon. I don't know what went wrong there, but I'd really love to know. Perhaps someone can translate his book one day. But Riccioli was convinced by everyone's data. He thought, well, maybe they're both right. Maybe what's actually happening is the comets are moving just everywhere, through the orbit of the moon, through the orbit of the planets, just everywhere. What certainly was true was that the motion of the comets proved that there were no crystalline spheres. The comet could move freely between the orbits of various objects in the sky. Lastly, we have this hand of God at the top, and it has the three fingers saying number, measure, and weight. Riccioli was not just talking the talk, he was walking the walk. He cared about his data. He was by all means an empiricist. And sometimes this was a problem. Here we have his measurement of the circumference of the Earth. He had a decent measurement. It wasn't as good as Snell's before him, but actually over time it became worse. He finally accepted the last measurement there. And the problem wasn't that he wasn't trying to measure it well enough. The problem was that he was trying to measure it too much. The Greek method, as you may recall, is the method of using the time the sun is above you and then measuring it from 2 points and then calculating the angle. The Arabs had a method where you climb the mountain and then you try to get a right angle through the horizon. And by calculating the angle on the mountain, you could calculate the shape of the Earth and size. Riccioli and Grimaldi preferred a method where you used two towers or a tower and a mountain. And in this way, you could calculate accurately the height of the tower and the mountain, and then measure the angle from the bases of them across the tops of the objects. And this actually required more measurements, but he thought it would be more accurate because they could measure all of it. And actually this ended up with a worse result. Fortunately, Cassini corrected it not long after. Another intriguing one is obliquity of the ecliptic. So this is the angle of the Earth against the ecliptic around which it spins. And this actually changes over time. But Riccioli took multiple measurements and was so convinced that his measurements were right that he decided that the kind of idea that others had suggested that perhaps it changes over time can't be right. Perhaps the people of the past were wrong. He had got three measurements that are exactly the same, and so surely it doesn't change over time. They were probably just mismeasurements before. The most famous bit of the Almagest no doubt, is the lunar crater naming. This was drawn from a map. It wasn't the first time that a map had been drawn of the moon. Before this, there was Van Langren, who had named craters on the moon after the people he hoped would give him money. And there had been Hevelius's map, where he tried to compare various objects on the moon with things on Earth. So what was Copernicus' crater on Riccioli's map was Mount Etna, and with Sicily around it in Hevelius. Why was Riccioli's map accepted? Most likely because the fact he used astronomers as the naming conventions for all of the craters. I think astronomers were quite happy with the prospect that they might end up on the moon one day. And something that he was criticized for sometimes was that you can't quite see it, but there is a Riccioli and a Grimaldi crater already in their first naming. Some thought this was a bit vain, that they put themselves on the moon. But certainly they picked small craters for themselves, and they put themselves right on the edge of the ocean of storms, this region where all the stormy characters went. Galileo, Copernicus, Kepler, the astrologers, that's where they went. Riccioli and Grimaldi measured other things to a very good accuracy. This was perhaps not the best, but it was certainly an improvement. We talked about diurnal parallax. This is something that Kepler measured to 1 minute. Riccioli and Grimaldi decreased it to 28 seconds. And Cassini, soon afterwards, working with them, decreased it to 10 seconds, which isn't far off the value we have today. So one of the things that Riccioli wrote about in the Almagestum Novum was he criticized Ignazio Dante's Meridiana. Why did he do this? This was because Cassini had already started using the Meridiana to try and verify Kepler's elliptical orbits. The way this was done was you would measure the apparent diameter of the sun and compare it over time. If it had a variation of 2 seconds. 2 seconds? No, 2 minutes. It was 2 minutes. 2 minutes. If it had a variation of 2 minutes, it would mean that it followed a path that didn't fit Kepler's model. If the eccentricity was bisected, which meant a 1 minute change only, this would mean that it was following an elliptical path. And Grimaldi and Riccioli took a measurement, and it kind of fitted within the 1 minute difference, but others of the time were also measuring it, and some of them found 2 minute differences. Now, Riccioli wrote that he cannot prefer his own data to those of others. In some ways, he was often quite trusting of other people's measurements, and so he decided, well, actually, there is clearly a 2 minute difference, at least, and therefore there can't be an elliptical orbit. And perhaps the problem was that Dante's Meridiana in San Petronio was just not accurate enough. And there were certainly problems with that Meridiana. It had been placed in an awkward position where there was a column in the way, so it couldn't actually be as long, as high as people wanted it to be. Another thing that Riccioli measured and Grimaldi was the length of the tropical year. Now, Heilbronn wrote that this was the most accurate of the time. I wasn't quite sure. That sounded a bit dodgy to me because the tropical year varies extensively. The tropical year is your time from equinox to equinox the year after, or from solstice to solstice. And this isn't very stable, as you can see with the graph on the left. But actually, when I took an average of the time from 1590 to 1651, the value was off by a second. And since the tropical year actually is increasing slowly with time, by the end of that time, it was actually more or less what their value was. And to get a value within 1 second in that period was phenomenal anyway. Riccioli is certainly remembered for his arguments against heliocentrism. And one of the criticisms made about him often is the fact that he wrote these 126 arguments for and against the Earth's motion. 49 were for the Earth's motion and 77 were against. They say, well, that's biased, actually, because he wrote more against heliocentrism. But for each of these arguments, he also wrote a counter-argument, and in fact, he discarded 124 of those arguments. The only things he really considered strong points were the fact that There was no stellar parallax, and there was no Coriolis effect, both scientific arguments. There were theological arguments and philosophical arguments listed, but he did not find them convincing. So let us look at stellar parallax. This was intriguing because Riccioli was the first to publish an observation of a double star. This was this double star Mizar. But he was not the first to have observed it. The first to observe it was actually Galileo through his telescope. And Galileo had measured it over a year to try and figure out if he could find stellar parallax himself. This would be undeniable evidence of heliocentrism. When he didn't find it, he just didn't publish it or mention it. And oddly, in his dialogue, he wrote that perhaps one day someone will find a double star and maybe they'll find some parallax and that will be proof of heliocentrism. He wrote this despite trying it himself and failing. Riccioli found Mizar by himself and considered this, the fact that there was no parallax, to be evidence that there was no motion of the Earth. There was, of course, another way you could interpret it. Perhaps there was no parallax because the stars were so far away. This is something that Galileo had argued. But with his measurement of the diameter of stars in his telescope, his prediction meant that even the lowest size of stars was magnitudes greater than the largest star we know today, Stephenson 218. It was a ridiculous size. The stars would have to be bigger than the whole known universe at the time, and most scientists could not believe something like this. Of course, now we know what the problem was. The parallax was smaller than they expected. The stars were further away, much further away. But the measurement, the naive measurement of a star's diameter in a telescope was faulty. What they were actually measuring was an airy disk, which is a diffraction pattern in a telescope, and not the actual diameter of the star. They realized this as telescopes got bigger, of course, as they got better, and the higher magnification you got, you still had point objects from the stars, really, frankly. So this was eventually dispelled, but certainly at the time, this was pretty convincing. Then we have the Coriolis effect. Riccioli did not provide a mathematical formula, but what he did was he ran a thought experiment, which was qualitative. The idea that when you fire a cannon upwards, or perhaps forwards, if the Earth was spinning, it should start to diverge from its path. Why? If you imagine the Earth is spinning, if you fire something in a straight line, it should continue along a straight path. And relatively to that Earth spinning, it should look like it's curving away. And the same effect should happen if you're firing something towards the equator from a higher latitude. Perhaps we should call the Coriolis effect the Riccioli effect. And I think that would be quite fitting, because Riccioli can be translated to mean curly. So it kind of works. While Coriolis neither was the first to suggest it, nor was he the first to build a good mathematical model for it, which I think could be attributed to Euler or another mathematician. And he certainly wasn't one to demonstrate it, because that didn't happen till Foucault's pendulum in 1851. What had certainly happened a long time before then was the mathematical models of Euler and others showed that the Coriolis effect was smaller than expected, and therefore that was why we couldn't see it. Riccioli said, well, we can't see this based on something that wasn't really proved, because at the time, cannoneers in the army said that they were so accurate that they could fire a cannonball up in the air and it would land right back in the barrel. And this was almost believed at face value. No one actually tried it. Perhaps good for their safety. In 1655, this is after the Almagest, we have the building of a new Grand Meridiana at San Petronio, which was one of the biggest ever built. It was 27 meters high. It was designed by Cassini, but it was given to be overseen by Riccioli and by Riccioli, Grimaldi, and another astronomer, Ovidio Montalbano. This was done at huge cost. 15% of the Basilica's income of that year was devoted to this. A year later, this was used to verify Kepler's elliptical orbits once and for all. And this was done by Cassini and then checked again by Riccioli and Grimaldi. And together they confirmed that indeed there was an elliptical orbit of the Sun. Now, this is a bit complicated, but frankly, when you have relative motion between two objects, whether it is circular or elliptic, it could be one orbiting the other or the other orbiting the first. So heliocentrists saw this as evidence that indeed the Earth moves around the Sun in an elliptical orbit, while geocentrists like Riccioli said, well, actually, all this shows is that the Sun is moving around the Earth in an elliptical orbit. San Petronio was a hotbed of great scientists, and no doubt Riccioli and Grimaldi were involved in building that team there, along with Cassini. There were 4,500 observations made from 1655 to 1736, 400 alone by Riccioli, Grimaldi, and Cassini. But others worked there who became great astronomers, did great things. Mengoli was key in building the gap between the mathematics of the time and the calculus that was to come. Montanari worked on variable stars, phases of Saturn, comets. Fabry worked on medical ephemerides, helping the doctors. I'm not sure that helped them that much, but certainly it was an impressive piece of work. Guglielmi worked on comets, optics, eclipses. Metsuvaca built ephemerides using all the models available at the time, which is quite a phenomenal bit of mathematics to do. And Manfredi is an interesting one. While you will probably know from previous lectures I've seen you've had here that Bradley was the one who found stellar aberration, which was the first empirical evidence of the Earth's motion. Well, buses and astronomers, they always come in twos and threes. Manfredi was another one who at the same time was looking at stellar aberration, and he found it and published it just a little too late. In 1663, we have Leverreur's Prodromus. And here he criticized the results in San Petronio, using Riccioli's arguments against him that meridianas were not accurate enough. And Riccioli wrote a letter back criticizing him. Cassini wrote back to Riccioli saying, "I love Leverreur, since the occasion of his writing gave rise to such a monument of your kindness towards me." This echoes the Christian Easter message of the happy fault of Eve and Adam, who deserved so great a savior in Christ. So this was both a sign of hatred for Leverreur and of love for Riccioli. And of course, the conclusion of the elliptical orbit was that the Sun moves around the Earth in an ellipse, and all the planets are moving in ellipses around that ellipse. This is Flavia Malcacci's model, and she's done some phenomenal work, so please do check out her papers. And in Astronomia Reformata, 1665, he wrote down a mathematical model that used this as part of his theory. The Sun moved along a conical path, which involved ellipses that rotated, and he vindicated the use of church meridians as a measuring device. And indeed, they were pretty accurate. A centimeter in the San Petronio floor was about a second of measurement in angle. However, this wasn't the end. He did have a few more scandals. In 1665, there was a misalignment of Easter once again, and this happened just before his publication. And there was a lot of criticism of the Gregorian calendar, which he, of course, had to defend. And then he was criticized by others who claimed that he didn't understand relative motion, that his whole argument of the Coriolis effect was ridiculous, and he had to defend it which he did in numerous papers. And the most awkward thing is around the time of his death, Mengoli discovered that the hole in the ceiling of the church had slipped by as much as 4% around the time it was built. So all the measurements must be off by quite a bit. There was a huge argument that ensued, with some claiming that it wasn't that much, and there was certainly a lot of debate as to what it meant for all the values. And Riccioli was interested in a lot of other things. He wrote on geography, on prosody. Prosody is the study of rhythm in poetry. And he wrote theological works. Twice, he ended up having problems with church censors. First in 1657, his book was stolen by the censor and not returned to him. He was very fortunate in that Cassini at the time went to visit the Pope to discuss a dispute over a river between two municipalities. And the Pope owned up that he was actually interested in astronomy and that he really liked Riccioli's Almagestum Novum, and that he built sundials in his spare time, as any Pope should do. And on hearing this, Cassini told the Pope, Alexander VII, about this situation with the censor who would not return Riccioli's manuscript. As a result, the Pope ordered the censor to return it, and he got it back. He wrote other texts, and intriguingly, in 1668, he also wrote on the immunity of error of the Church in their decisions around making saints, feast days, and so on. But his book was not immune from error. It was put on the index. One of his other great books is his Chronologia Reformata, which is a historical book which labels every important person that ever existed from the beginning of time, which was, of course, in about 6000 BC. And in there, that is where I found his labeling of Theseus and the Minotaur. So very interesting book as well. Anyway, I've got one last thing. I think we should really finish up. I think people have trains. But here's an intriguing thing. A guy called Holger Eisenberg reached out, and he was intrigued by the fact that Galileo had been put down as a crater in just there, in Riccioli. Now, that crater turned out to not be a crater. It is now what is called the Rhina Gamma, which is a luminescent feature of the moon. In Langren, it was not labeled. That's Hevelius. No, that's Hevelius. That's Sicily. So that's Hevelius, not labeled. In Langren, he was named after Ismael Bullio. But when it was discovered that this was not a crater, this was by Beer and Madler, who we've heard about today. They were labeling only craters, and they did not want this to have a name. So it ended up having a name of the most local crater, which was the Rhina crater. Galileo was put somewhere else, a small, obscure crater no one could barely see. And Holger's interest is that this Rhina Gamma has actually become interesting again. We now have the Lunar Vertex mission landing there because there have been discoveries of geomagnetic activity in the region, and it has become interesting again. And Holger was wondering, should we rename it again? Should this be called the Galileo Gamma, the Galileo Impulse? What should it be? Certainly, he should get this wonderful piece of the moon that has become interesting over time, that has been vindicated, just like he was. And that's it. I have recommendations to make. Heilbronn's Sun in a Church covers the 1600s really well in terms of what observations were being made at the time. Graney's Setting Aside All Authority really well describes the science of the time and why there was opposition to heliocentrism quite late in the 1600s. Flavia Marcacci, whose animation we showed earlier, she's written one in Italian. If you're bilingual, that would be great for you. And of course, my book, my translation is, I think there's still a copy at the back, but it's all right. And please do check out, there are papers by Graney and Marcacci which cover a lot of really interesting aspects of this period. So, and I thank Graney especially very much. He's been checking my translation with a fine tooth comb. So it's yeah, I think that's it. So thank you very much. I don't know if there's time for questions, but.
Fascinating stuff. Carolyn sends her apologies. Just as you started talking, she got a text from the roller to say her latest tremors cancelled. She had to leave in a hurry.
Okay.
So let's take a couple of questions.
Quick one. Thanks, I enjoyed that. Particularly interested in the Church Meridian, which I've not heard of. So I'll have you for that. You said there was a difficulty choosing the date. I always thought that was just the first Sunday after the first full moon after the spring equinox.
So yes. However, before the Gregorian calendar, we had the Julian calendar, and the Julian calendar assumed that a year was exactly 365 days and a quarter. And over time, what would happen is this shifted away from the actual spring equinox. And calculating the actual spring equinox is not so easy because, as we saw, the tropical year differs every year by quite a bit. So, yeah.
Nobody else. How did the church, the hole in the church roof, slip?
So I'm not entirely sure, but I imagine it's pretty structural.
Italian
I'll edit that out of my video, but.
Okay. Any more? Well, thank you so much, Michelle. I'm sure Riccioli is not somebody that I knew particular amount about, but it does turn out he was a very significant figure. The way that he's, the things that like the Coriolis was that he came up with, which are profound, but at the same time, why did he stick with centrism for so long? Well, to answer the question, there was an intellectual battle going on. People took different sides in it for intellectually good reasons, and we see those battles playing out in the century. Absolutely fascinating stuff. So give her a